Pathak sir, good evening.
Good evening.
Anirban, good evening.
Good evening, Dipamada.
Yeah, okay.
Good evening. So we still have about five minutes. The talk is scheduled at 7:30. So I hope some more people will join by then. And YouTube streaming has already started. Yes, yes. Talk is from 7:30 Indian time. 7:30 Indian time.
Hi, everyone. Can't hear you.
I was muted. Means Professor Leggett is yet to join. We'll start soon.
Yeah, okay.
Hello, can you hear me?
Yes, Professor Leggett, you are audible. Welcome, Professor Leggett.
Yep. Hello. Okay, so everything looks like it's in order. You have the screen sharing set up, I guess. So, yeah.
So, will you share your screen or I will show the slides?
No, you have to do it. I can't do it.
Okay. Yeah. Okay. So it is still 3 minutes to 7:30. So we wait for 3 minutes and then we start.
Yes, sure. Okay.
सर आप है ना लॉगिन? हाँ, हाँ। Good evening, everyone who has joined from India, and good morning to those who have joined from US, including Professor Leggett. And we're going to start. And at the beginning, I would like to request Professor Anurag Sharma, Professor Emeritus at Indian Institute of Technology, Delhi, and he is also chairperson of the NASI Delhi chapter, to say a few words about the activities of NASI as a whole and NASI Delhi chapter in particular, and to welcome the dignitaries and Professor Leggett. So Professor Anurag Sharma, please.
Yeah. So good evening, good morning. Good morning, Professor Leggett. It's my honor and pleasure to welcome you for this seminar or webinar, as we have been calling it these days. And it's really a pleasure that we will be able to hear you on a very important topic of modern technology, I would say. You know, it's going to be a technology really in the near future. I welcome you on behalf of the Delhi chapter of the NASI. NASI is the National Academy of Sciences in India, which is actually located in Allahabad. But it's the first academy that was started in India by Professor Meghnad Saha, who was well known for his ionization equation, which is extremely useful for astrophysics and many other areas. And this academy holds large number of activities like any other academy, but particularly is interested in reaching out to the young children or students in universities and colleges. That's one of the major activities which we can say that in the form of outreach. And that's really where it excels, and also does many other activities which the academies do. And there's a large fellowship of that in India and quite a few abroad. The Delhi chapter of NASI was established in 2008, and since then it has been doing very well in organizing outreach activities, seminars, projects in colleges, and outreaching to the students in various colleges and so on. My predecessor, Professor Ghatak, who is also in the audience today, ran it very, very well, and I'm just taken over from him. This is the first event actually under my leadership, I would say, and I hope to sort of match what he did in all these years. He's my guru. I mean, I did PhD with him, so I have learned a lot from him, and I'll continue to learn. So he's also there in the audience. Welcome, sir, to this particular seminar. So with those words, I welcome Professor Leggett again, and we look forward to hearing you. Anirban, yeah.
Thank you, Professor Sharma. And before we move to Professor Leggett's lecture, I would like to request Dean of Academic and Research, JP Institute of Information Technology, to Professor D.K. Rai to say a few words and welcome Professor Leggett and all the guests who are present today. Professor Rai, please.
Thank you, Professor Anirban. Nobel laureate Professor Anthony J. Leggett, all the dignitaries and participants, a very good evening. I, on behalf of JP Institute of Information Technology, Noida, extend my warm welcome to Professor Sir Anthony J. Leggett and all present in the webinar. It is indeed a matter of great pride for us to organize this event jointly with National Academy of Science, Delhi chapter. JP Institute of Information Technology, located in Noida, which is close to Delhi, is a multidisciplinary deemed university established in 2001 by Jayaprakash Seva Sansthan, with the vision of becoming a center of excellence in education, training and research in the field of information technology and other emerging areas. Institute offers graduation, post-graduation and doctoral programs in computer science and engineering, information technology, electronics and communication engineering, biotechnology and management, and post-graduation and doctoral programs in mathematics, humanities and social sciences, physics and material science and engineering. Institute strives to promote research in frontline areas in all disciplines of engineering and sciences. I'm particularly pleased to mention that we have an active research group working on quantum information and quantum communication, which is very, very close to the topic of today's webinar. I hope this webinar will be highly inspiring for all the participants. Thank you very much. Thank you all.
So thank you, Professor Rai. And now the last thing means it's my pleasant duty to introduce Professor Leggett before his talk. So of course, all the people who are in audience knows about him, but there are some students in the YouTube channel who are watching from live streaming. They may not know about Professor Leggett. So I'm just briefly telling them that at present, Professor Sir Anthony J. Leggett is John D. and Catherine T. MacArthur Professor at Center for Advanced Study. And he's also Center for Advanced Study Professor of Physics at the University of Illinois, Urbana-Champaign. He is a world leader in the theory of low temperature physics, specifically on the theory of superconductors and superfluids. For his pioneering contribution into these two fields, superconductors and superfluids, he has been awarded 2003 Nobel Prize. He was also knighted in 2005. That is, he received Order of British Empire from no other than Queen Elizabeth II. He is also fellow of Royal Society and various academies and societies of importance, including National Academy of Sciences, not to confuse with the National Academy of Sciences, India. He is also fellow of American Physical Society, Institute of Physics, Russian Academy of Science, etc. And apart from Nobel Prize, he is also recipient of various other prestigious awards like Simon Memorial Prize, Paul Dirac Medal and Prize, Maxwell Medal, etc. The list is too long and it's not, you are waiting to listen his talk, so I'm not extending that list, but it's important to mention that his interest in research is very broad and which includes but not restricted to superfluidity and superconductivity, foundational aspects of quantum mechanics, quantum information, etc. So with this brief introduction, now I would like to request Professor Leggett to deliver his talk, and I would also request others to kindly mute their mic. So Professor Leggett, I'm sharing the slide.
Okay, good, thank you. Well, good evening, everybody. In 1964, a little over a half century ago now, there appeared a paper in a journal which was so obscure that it went out of business within the year. It was by an author who, although he was relatively well known in his specialist field, was certainly not a household name in the physics community, much less to the general public. And the paper was on a subject so obscure that I believe I'm correct in saying it got no citations whatever for the first 5 years of its existence. Gradually, people started to realize the importance of the theorem, Bell's theorem, which was proved in this paper. And So now the ideas which have stemmed from that have probably received hundreds of thousands of citations in the literature, and they're the foundation of a multi-billion-dollar industry. And incidentally, the theorem in question, Bell's theorem, is probably the only theorem which has a street named after it anywhere in the world. It actually does have one named after it in John Bell's native Belfast. So I'm going to try to give you at least a brief explanation of why this theorem is so incredibly important and why it's had such an enormous impact. I'll start off with some elementary considerations on classical electromagnetic radiation and photons, which I hope you're all familiar with. I'll go on to talk about Bell's theorem itself and what stems from it, the general notion of entanglement. I'll talk about some applications, and if time allows, I'll talk about a slightly more specialist topic within this general topic, which I have been particularly interested in myself, which is so-called superconducting qubits. Okay, could I have the next slide, please? Could I have the next slide, please? Thank you. Okay, so here are some elementary considerations about classical light waves and photons. As I say, I trust that most of you are already familiar with this material. Suppose we have a classical light wave propagating into the screen. Then there are at least two possibilities for its so-called polarization. The direction of the electric field can be in either the X or Y directions, perpendicular to the propagation vector. And so in these two cases, the electric field as a function of space and time is given by the two formulae which you see. Now, a very important principle of classical physics is the idea that you can superpose two different possible solutions to the wave equation. So you can put together an electric field E sub x and one which is E sub y, and by doing so you generate an electric field which is the vector sum of those two and is in some different direction in the plane. So you, in this case, you find that the correct expression for the electric field is the real part of Exx plus Eyy, etc. No, please stay on the first slide. Please stay on slide 2. No, please stay. Please go back to slide 2. Thank you. Yeah, that's right. That's right. Correct. Yeah. Thank you. So you have this this solution which it describes an electric field at some angle in the xy plane. It's also possible to choose E sub x and E sub y, the two components, to be complex. In which case we get, for example, an electric field which is proportional to x plus Iy times exponential ikz minus omega t, which you can write out in the second form below. So crudely speaking, if I have that kind of electric field and I sit at a particular point in space, what I see is the electric field rotating as a function of time, either clockwise or anti-clockwise. And it turns out, and perhaps not too surprisingly, that this kind of field carries a finite amount of angular momentum. And there's some very beautiful experiments which go back more than a century which verify that. Now imagine that a light wave described in this way falls on a so-called birefringent crystal or polarizer. What do we mean by that, a polarizer? What we mean by polarizer is that it is a crystal such that if, for example, the electric field is along the x-axis, vertical axis in the diagram, then the wave will be totally transmitted. If, on the other hand, the electric field is along the y-axis, then the wave will be reflected or more likely absorbed. It doesn't really matter which. So what this means is that if I have now an electric field at an arbitrary angle in the xy plane, as I do in the diagram there, the transmitted part is the x component, which is given by the magnitude of the field times cosine of theta, the angle with the x-axis. So that's the transmitted amplitude. But as you know, the energy of the wave is proportional to the square of the amplitude. So that's proportional to E sub x squared, which is E squared cos squared theta. Now the initial energy before it hit the polarizer was just a total E squared. And what that means, therefore, is that the fraction of energy transmitted is simply cosine squared of theta, where theta is the angle which the field direction makes with the x, the transmission axis. And that is a famous law which goes back to the 19th century, known as Malis's law. Okay, next slide, please. Thank you. Now, eventually we have to describe the electric field in terms of quantum mechanics. And in quantum mechanics, the notion of the electric field, the classical electric field, is replaced by the notion of photons. And you may think of the photon as the minimum packet, as it were, of the electric field which can exist in free space. And it turns out that there is a quantum mechanical amplitude psi which corresponds very closely to the classical field amplitude E. And you remember that in classical physics, if we had two different solutions of the wave equation, we were allowed to superpose them. That's also true in quantum mechanics. If psi1 and psi2 are two allowed quantum mechanical amplitudes, then so is the superposition alpha psi1 plus beta psi2. For example, if psi1 is a possible solution that's denoted by x, that corresponds to a single photon polarized along the x-axis, and psi2 is y, corresponding to a single photon polarized along the y-axis, then we can put them together with arbitrary amplitudes to generate a wave function which represents a photon, single photon, with linear polarization at an angle theta in the xy plane. And similarly, if I put them together with a complex relative amplitude, then I get something like x plus iy, and that again describes a single photon with right or left, clockwise or anti-clockwise circular polarization. And it turns out, perhaps again not very surprisingly, that a single photon, which is circularly polarized, carries an angular momentum plus or minus h bar in the direction of propagation of the wave. We'll need that result later. Now, what happens if a single photon is incident on a birefringent crystal? Well, if the photon is polarized entirely along the x-axis, then it will be simply transmitted. If it's polarized along the y-axis, it'll be totally reflected or possibly absorbed. But what if it's actually that photon, that single photon, is actually polarized in the xy plane at some arbitrary angle, theta? Well, a photon can't be split, at least not at the kind of level of discussion we're doing right now. It is actually a slightly more complicated subject, but at least for present purposes, no, you can't split the photon. So what happens? Next slide, please. No, I think there's a slide in between, isn't there? Slide 4? Yeah, right, thank you. Good. Okay, we're asking what happens when a single photon is incident on a polarizer by a refrigerant crystal. It has to remain as a minimum bunch of the electromagnetic field, so it can't be split. It has to be either transmitted or reflected. And the result is, the correct statement is, that the probability of transmission is equal to cosine squared of theta. So it's 1 if the photon is polarized along the x-axis, 0 if it's polarized along the y-axis, and well, cos squared theta for the directions in between. And that's the quantum version of Mavis's law. Now, I might ask, can this behavior be explained by some kind of classical probabilistic theory? And the answer is yes. It turns out there's actually a rather simple way of doing that. Suppose we imagine that when the photon has a nominal polarization given by the blue arrow in the diagram in the middle of the slide, it is in fact characterized by some hidden or true polarization variable which is distributed at random around the nominal polarization. And then we simply imagine that if now there's actually, I'm afraid, a typo at this point. The true polarization should actually be a black arrow, not a blue arrow. And so if the black, it doesn't come out. So if the black arrow is closer to the transmission direction, the photon will be transmitted. If it's closer to the reflection direction, it'll be reflected. And if it's transmitted, then to make everything consistent, you have to readjust the distribution of the hidden variables. And it turns out it's a rather simple piece of algebra, that if you choose the random distribution to have the form which is written in green at the bottom of the slide, then this simple classical statistical model can reproduce the quantum version of Mavis's law. So at least at first sight, it seems there's no particular reason to think that quantum mechanics has introduced any special feature here. Next slide, please. Okay, but now let's go on and think of something a little more complicated. Suppose we have a set of atoms which are excited by maybe some kind of spark discharge and decay back to their ground state. And we'll suppose that the decay back to the ground state is actually a two-step process via an intermediate state, and that in that process, two photons are sequentially emitted. So the transition of the atom from the upper level to the intermediate one emits photon 1, and then as the atom goes from the intermediate state to the ground state, emits photon 2. And let's just imagine that they're emitted back to back, although that's not the only possibility. Well, we can ask ourselves, what is the correct description of the polarization state of the photons? Well, you recall that x plus iy, the wave function, photon wave function, x plus iy, corresponds to photon angular momentum plus or minus h bar. That is, to an angular momentum along the direction of propagation, which is either clockwise or anti-clockwise with magnitude h bar. And I've noted, I'm going to consider a specific kind of process in which both the excited, the initial state of the cascade decay, and the final state both have angular momentum 0. That's the 0 in the labeling of the diagram. Don't worry about the plus for the moment, we'll come back to that. Now, it's a very important principle of quantum mechanics. Here, let me just skip ahead for a moment. In this case, because the total change, the atom has changed its total angular momentum by 0, that means that the total angular momentum of the two photons must be 0. However, we don't know whether photon 1 carried off plus h bar and 2 carried off minus h bar, in which case the intermediate atomic state has angular momentum -1, or vice versa, with the intermediate state being m equals +1. Now, it's a very general principle of quantum mechanics that a process can happen either of two ways, and we don't and can't know which way it happened, then we must add not the probabilities, but the amplitudes for those two processes. That's perhaps the most basic principle of quantum mechanics. And therefore, in this case, we must take the wave function x plus iy for photon 1, x minus iy for photon 2, which corresponds to photon 1 carrying off h bar and photon 2 minus h bar. And we must add that to the second possibility, which is that photon 1 had angular momentum minus h bar, and photon 2 had plus h bar. And very crucially, in general, there's going to be some phase factor between those two amplitudes. Now, this is where the plus comes in. This is a slightly technical point, which I suspect not all of you may have met in detail, but it turns out that because both the atomic states have positive parity, that guarantees you that the phase factor is just +1. So psi is given by the expression in blue, with the phase factor being +1. And so now we can just do a bit of trivial algebra and rearrange that so that we now write it in the form of the bottom, the last formula on this slide. Apart from normalization, the total wave function is just a quantum superposition of a state in which both photons were polarized along the x-axis and a state in which they were both polarized along the y-axis. Okay, next slide, please. Okay, so that's just to recap. That's the correct description of the two-photon wave function when the two photons are emitted in this kind of cascade transition. So what this means is that if photon number 1 is measured to have polarization X, then automatically so will photon number 2 have that same polarization along X. If on the other hand, if photon 1 has polarization along Y, then again, automatically so will photon 2. However, there's something peculiar about this, because this state actually turns out to be rotationally invariant if I express it in terms of a new set of axes, x prime and y prime, oriented at 45 degrees, as you see there, then the photon wave function looks essentially exactly the same in terms of the new variables. And so what that means is that if 1 is measured to have polarization x prime, so will 2. If 1 is measured to have polarization y prime, again, so will 2. It's very important to realize that is not true for what you can call a classical mixture of x1, x2, and y1, y2. That is, for a state in which each particular pair of photons definitely either has both the photons emitted along the x-axis or has them both emitted along the y-axis. That will not give you this kind of rotational invariant behavior. This is entirely a consequence of the quantum mechanical principle superposition of amplitudes. Okay, now let's ask, what happens if photon number 1 is incident on a polarizer with transmission axis A, and photon number 2 is incident on a polarizer with a differently oriented, this should be transmission type of a transmission axis B? Well, the choice of axes for the two-photon wave function is arbitrary. So let's choose x to be along the a-axis. Then the probability of transmission of photon 1 will be the square of its weight in the wave function. That's the square of 1 over root 2, a half. So the probability of 1 being transmitted is a half. But if 1 is transmitted, then that automatically means the polarization of 2 has to be A. So now, if that second photon is incident on a polarizer set in the direction B, different from A, then the transmission probability will be given by the quantum version of Madison's law. It is cosine squared of theta AB, the angle between A and B. So putting those together, the probability of both photons being transmitted through their polarizers is a half cos squared theta AB. Next slide, please. Okay. Yeah, let's see. Right, that's right. Yep. Okay, so now then consider this experiment in which the atomic source undergoes this cascade decay, and photons 1 and 2 are emitted and are submitted to a polarizer with appropriate transmission axis, followed by a detector. And again, I'm sorry, I apologize, there seems to be another typo in the green box. It should be probability of both detected, not deleted. So the probability that both photons are detected in their respective detectors is a half cos squared theta AB. The probability that neither is, again, detected, it's a half cos squared theta AB. And the probability that 1 is detected but 2 not, or vice versa, a half sine squared theta AB. Those are the predictions of standard quantum mechanics for this particular kind of photon state. They're not the predictions you would get for a so-called isotropic mixture. But by isotropic mixture, I mean that the photons, the pair of photons emitted in each particular by each particular atom is definitely is the same, but is in a definite direction. That description would give you a crucial extra factor of a half in the formula there. But anyway, as I say, that's not what quantum mechanics gives. What quantum mechanics gives is the formula in the green box. Now, we saw that in the case of a single photon incident on a polarizer, then the results could be explained by classical probabilistic theory. But can they in this case? Well, to examine that point, we need to introduce a little notation. Let's suppose that for a given pair with polarizer 1 set at direction A, then that photon 1 is detected. Then we say that by definition for that particular photon, the variable capital A is +1. If on the other hand, again with the polarizer 1 set at A, the photon is rejected or reflected, then the variable capital A is -1. Similarly, polarizer B 2 set at B, photon 2 is detected, then B is +1, and if it's rejected, then B is -1. Then the statements within the green box are equivalent to the statement that for the average over the ensemble of pairs, the expectation value of the product of the variables A and B is given by cos squared theta AB minus sine squared theta AB. That's cosine twice of theta AB. Again, just note, if you had a classical mixture of different polarizations, you get a crucial extra factor of a half there. So, for example, for special cases, if the two polarizers are set parallel, theta AB equals 0, then the expectation value of AB is +1. if they're set perpendicular, then the expectation value of AB is -1. And that, crudely speaking, is that what was noted many years ago by Einstein, Podolsky, and Rosen in their famous paper on this subject. And in fact, these two, it turns out, perhaps not immediately obviously, but it turns out these two special cases can in fact be accounted for by a classical probabilistic model. However, what Bell saw was that it's actually a little more complicated than that. Next slide, please. Next slide, please. Okay, good. So again, let's just, it's a bit tedious, but let's just make a few definitions. Imagine now that I've got my atomic source, I send out my photons 1 and 2, but now I pretty the experiment up a little by arranging that I have a switch, which, for example, can switch photon number 1 into either of 2 counters. The counters basically consist of a polarizer set in a given direction, a given transmission axis, followed by a detector. And the crucial point is that the transmission axis for the measuring stations, the detectors A and B, is in general different. Again, as we did this already on the last slide, let's say that if photon number 1 is switched into counter A, and then if counter A clicks, then the variable A is +1. If counter A does not click, then A is -1. However, notice that if photon number 1 was switched into counter B, then A is simply not defined, at least so far. What can experiment measure in this situation? Well, it can measure the correlation of A and C on one set of pairs, namely those for which photon number 1 was switched into counter A, photon number 2 was switched into counter C. It can also measure AD, the expectation value of A times D, on a different set of pairs, namely those for which, again, 1 was switched into A, but now 2 was switched into D. That's different from the first set, etc., etc. Now, a quantity, it's not quite immediately obvious why, but a quantity which turns out to be of rather special interest is what I'll call K sub X experiment, which is the sum of the first 3 correlations, AC plus AD plus BC, minus the 4th correlation, BD. For that quantity, quantum mechanics makes clear predictions. Next slide, please. Okay. Well, we'll come back to the quantum mechanical predictions, but now, just let's digress for a moment, as Bell essentially did, and consider a class of theories about the world, which we can call objective local theories. And objective local theories are defined by the conjunction of 3 postulates. The first postulate is local causality in the sense of Einstein's special relativity. That means that no causal influence can propagate faster than the speed of light. The second postulate is the normal arrow of time. That is that the past can affect the present, and the present can affect the future, but not vice versa. The third is a little more tricky. You can formulate in one of 2, or at least one of 2 ways. We can talk about microscopic realism, meaning that photons have definite properties irrespective of whether those properties are measured on them or not. Alternatively, what I rather prefer to do myself, we can talk about macroscopic counterfactual definiteness. And I'll come back to that in a moment, but crudely speaking, that means that we can treat the outcome of an experiment which we could have conducted but chose not to as a fact about the world. That hypothetical outcome. And now with these simple ingredients, we can prove Bell's theorem. I would like to just briefly go through the proof just to show you there's nothing at all complicated about it. It's all every step in this argument is very, very simple. Step one, for each photon number one, this follows. Now I'm now invoking postulate number 3. Whichever version of postulate number 3 we use, for each photon number 1, then either the variable a is +1 or it's -1, independently of whether or not a was actually measured. Because remember, the result I would have got had I measured it is supposed to be a fact about the world in this objective local theory. Postulate number 2, this follows from local causality. The value of a for any particular photon number 1 is unaffected by whether it's C or D, which is measured on the corresponding photon number 2. Thirdly, putting 1 and 2 together, for each pair, the quantities AC, AD, BC, BD exist, with A, B, C, D taking the values plus or minus 1, and crucially, A is the same in the combination AC as it is in the combination AD, etc., etc. Given that, then simple algebra then shows that for each pair, the quantity AC plus AD plus BC minus BD must be less than or equal to 2. That's really trivial, almost grade school algebra. There are only 16 possibilities. You can just write them all out and see that that's true. Therefore, for a single ensemble, the ensemble averages must also satisfy that same constraint. However, there's a slight glitch here because you remember that strictly speaking, the ensemble on which I measured AC is not identical to the ensemble on which I measured AD. But at this point now, one invokes postulate number 2, the arrow of time. The properties of the ensemble must be determined by the initial conditions and not by the particular measurements I chose to make later. And therefore, you should identify the ensemble averages with the experimentally measured ones. That's the most tricky point. You have to think about that a little to convince yourself that that works. But in fact, it does work, and therefore, I think we can finally draw the conclusion that the measurable quantity, the K experimental, which is the sum of the difference of the 4 I've written down, that will satisfy an inequality, which is on the next slide, please. Next slide, please. Yeah. So it will satisfy the inequality in the first line of this slide. The experimentally measured value of K should be less than or equal to 2. You say, okay, what's the big deal? What's so peculiar about that? Well, what's peculiar is that that's not what quantum mechanics says. If we take the specific case where the polarizer settings are A, B, C, and D, as shown in the diagram, then, for example, for a 0+ transition, we've already seen that we predict that the expectation value of AC is cos 2 theta AC dot C, etc. And therefore, for the particular case I've drawn, where the A, B, C, and D are arranged in the way given with a 22.5 degree angle between them, quantum mechanics predicts that the experimental value of K is 2√2. Now, 2√2 is clearly not less than or equal to 2. And therefore, the experimental predictions of quantum mechanics are incompatible with those of any theory embodying these 3 principles: local causality, the arrow of time, and let us say macroscopic counterfactual definiteness. And that is essentially Bell's theorem. It isn't exactly what Bell proved in his original paper, but it's a development of it, which was done by others a few years later. It's essentially Bell's theorem. Well, before we go on to examine the consequences of this, let's ask, well, each of these postulates at first sight looks rather reasonable. Which are we going to reject? If we reject local causality, the whole structure of special relativity crumbles, so most physicists don't want to do that. We could consider rejecting the principle of the arrow of time, but then it seems very difficult to even be able to plan to set up an experiment. So again, I think most physicists wouldn't like to do that. So what about the third principle, macroscopic counterfactual definiteness? Let's consider once more the situation in which a given photon, say number 1, was in fact switched into counter B, so that at first sight at least the variable A is not defined. However, let's consider the possibility that the counterfactual possibility that we had switched that photon into counter A rather than counter B. Considering that hypothetical situation, we can now make one of two statements. And I don't think this is a glitch of a particular quirk of the English language. Those of you who are whose native language is not English might try to translate it into your native language and see if it still makes sense, and I bet it does, in fact. So, statement number 1 is in that hypothetical situation, it is a fact that either A would have clicked or A would not have clicked. I mean, since every time you do switch a photon into counter A, one of those two things happens, that seems almost a tautology. However, let's consider a second statement. Either it is a fact that A would have clicked, or it is a fact that A would not have clicked. Is that the same statement as 1? I don't think it is. And in fact, it's 2 that is the statement of macroscopic counterfactual definiteness. And this is rather nicely summed up in the title of a paper, short paper by the late Professor Asher Perez. The title of just to start that for one moment, please. Please, yeah, thank you. The title of the paper is simply "Unperformed Experiments Have No Results," and clearly it's a very subjective matter. But I think most physicists who have to cope with this situation would actually go for that solution. You simply cannot talk about the possible, the hypothetical outcome of an experiment which you did not, in fact, perform. Incidentally, one thing I should emphasize, said the experimental predictions of quantum mechanics are incompatible with those of any local realistic objective local theory. Since the original work of John Bell in 1964, there have been literally hundreds of experiments done on this situation, and with very, very few exceptions, which I think are well understood, they all give the quantum mechanical predictions. So we do have to reject the class of objective local theories. Okay, so that essentially is Bell's theorem, and the fundamental thing it tells you about the nature of the physical world. Let's go on to now explore a few related concepts. Next slide, please. Okay, so a very closely related idea, which actually predates Bell's work, is the idea of entanglement. Suppose we have a system composed of two separated subsystems, 1 and 2. Then, in general, in quantum mechanics, we can write down a wave function for that system, or at least we may be able to, under certain conditions. And rather generally, that wave function is a function of the variables of both 1 and 2. But now there are two possibilities. The first and rather boring possibility is that the wave function is factorizable. That is, it's a product of a chi of 1 times a phi of 2. In that case, we say it's a product or non-entangled state. In this situation, the properties of system 1 are described entirely by chi 1. The properties of 2 are described entirely by phi of 2. And complete information on the system can be obtained by making measurements on the subsystems separately. So that's rather boring. The alternative state of affairs is that what we call an entangled state, that psi of 1 and 2 is not simply the product of chi of 1 and chi of 2. For example, you've already seen an example of that in our two-photon state for the cascade decay of the atom. In that case, we saw that psi of 1 and 2 is actually given by the formula x1, x2 plus y1, y2, or if you like, up 1, up 2 plus sideways 1, sideways 2. And that cannot be simply factorized into a product of something referring to 1 and something referring to 2. And under those conditions, subsystems 1 and 2 don't possess individual properties. If you like, that's a possible version of Bell's theorem. And complete information on the system is can be obtained only by correlated measurements on 1 and 2. In other words, the information storage is non-local in such a state. And that has a surprising variety of possible applications. Next slide, please. So I'll just very briefly try to review some of the more spectacular consequences of the idea of entanglement. Okay, so let's start off with what is often called quantum teleportation. The rules of the game are that one player, Alice A, is to transmit to Bob B an arbitrary state of a single photon without direct physical contact. Alice may not even know what state she has sent, but she's got to be able to transmit that photon to Bob without any direct physical context. However, Alice and Bob, or more practically their surrogates, Claire and David, C and D, may communicate with one another by a classical phone line. That's allowed in the game. So how does this work? How does the idea of entanglement allow you to do that? Well, let's go to the next slide, please. Yeah. Incidentally, are you hearing me okay? Dr. Pathak? Are you hearing me okay?
Yes, it is perfectly okay. You are perfectly audible.
Good. Because there's a notice on my screen which says something about the audio quality. That's why I asked. Okay, fine, good. So yeah, fine. Stick there. Right. So the solution is that Claire C emits a so-called EPR pair. D receives that pair together with the photon sent by Alice. So D receives a pair of photons denoted by the red and green arrows. Now he may find them to be an EPR pair, or he may find them to be something else. If he finds them to be an EPR pair, then angular momentum conservation implies, and it's fairly straightforward to see this, though it takes a moment or two. It says angular momentum conservation at the site of Claire and David means that the state received by Bob is exactly the state sent by Alice. And so if D does in fact find an EPR pair, he simply picks up the classical phone line, telephones Bob, tells him that, and so Bob then knows exactly what photon Alice has sent. If D finds a state which is not the EPR pair, he can always rotate it into an EPR pair, and then he phones Bob, and Bob then performs the inverse of this rotation and again recovers the photon sent by Alice. Perhaps that doesn't seem all that useful or spectacular, but let's go on to the next. It certainly is nowhere near teleportation in the sense of Star Wars. That's a long way distant, but it's quite interesting. But anyway, let's go on to the next application. Next slide, please. Okay, this is really much more practical. Quantum cryptography. In classical cryptography, the central problem is the so-called key distribution problem. Alice must be able to communicate the key to the code that they will use to Bob. The key is a string of ones and zeros. And moreover, she may or may not be able to stop an eavesdropper, Eve, listening in. But if Eve is listening in, then Alice and Bob ought to be able to be aware of that. And classically, there's no 100% secure way of ensuring that. Now, what about quantum cryptography? Let's try to get rid of this. Yeah, good. Okay, how does that work? Well, we imagine we have a source S, which again will emit a string of EPR pairs. And now what Alice is going to do is to measure the pairs in one of two bases, and she chooses this at random for each pair. One basis is simply horizontal vertical, and the other is 45 degrees minus 45 degrees. And so she chooses the basis in a random way. Bob similarly measures also at random. After having done a certain number of shots, Alice and Bob inform one another by phone which basis they've used for each measurement. They discard those for which they use different bases, and they compare notes on a subset of the rest. Now, if they always agree, they can be sure of no eavesdropping. We'll come back to that in a moment. Then they can use the rest of the shots for the actual key itself. Now, why can they be sure of no eavesdropping? Well, suppose that Eve tries, for example, to listen in. Well, first of all, Eve can listen to her heart's content on the classical phone line, and this won't do her any good. What if she tries to listen in on the quantum channel? That is, she tries to intercept, say, the photon sent by S to B. Well, she can intercept it, fine. But now, can she send it on without distorting it? Here there's a very famous theorem, the so-called no-cloning theorem, which says that it's impossible to have a device which measures the state of a single, arbitrary state of a single photon, and then transmits that unchanged. It's a rather straightforward theorem, and it does always work. And therefore, if Eve tries to listen in, the photon which Bob receives will not be, or not always be, the one that S sent, and then the correlations between the measurements of A and B will not be 100% right, and they know that something has gone wrong. So this is actually a much more practical business. Already, some of my colleagues have used this scheme for, or a close to related scheme, not exactly this one, for demonstration purposes. Anton Salinger in Vienna, I believe, used quantum cryptography for a bank transfer a few years ago already. Nicolas Gissin in Geneva used it to transmit the results of a Swiss by-election down to the central counting station, and so forth. Of course, those are just sort of box office demonstration experiments, but they do show that things work. Okay, and in fact, some journalists have speculated, and I think it's not totally absurd speculation, that the really, really secure communications of the US government, for example, the line between the White House and the Pentagon, are actually being done right now by quantum cryptography. As I say, it's speculation. We don't know if it's true or not, but it's not implausible. Okay. Next slide, please. The final application I want to discuss is quantum computation. And to illustrate that, let's consider a set of particles that spin a half. Now, a single particle spin a half in a pure quantum mechanical state is parameterized by two independent variables, for example, corresponding to the angles made by the spin with the z and x axes. And therefore, a collection of n particles of spin a half in a product state is parameterized similarly by two independent variables for each, and that means the total number of variables I need is twice n. However, the same collection of n particles in a generic entangled state requires for its parameterization not 2n, but 2 raised to the nth power variables. For example, let's consider the case n equals 3. The wave function is the general function of the variables 1, 2, and 3, and it has a component corresponding to 1 up, 2 up, 3 up, another component corresponding to 1 up, 2 up, 2 down, up, 3 down, 1 up, 2 down, 3 up, etc., etc. You can see that there are 8 possibilities, in fact, 2 to the 3. So what this means is that you can have a massively parallel computation. Now, at first sight, there's an obvious objection to this, because, and this objection is sometimes made by people who I think actually should know better to the whole idea of quantum computation. The objection is that, okay, I can arrange for the system to go through all these fancy states, but at the end of the day, I've got to make a measurement of which of these 2 to the n states it's in. That's only one state, and I lose all information about all the 2 to the n minus 1 other states. The reply to that objection was figured out by people like Deutsch and Shaw. What you do is you set up your computation in such a way that depending on the answer to your question, it simply ends up in one and only one of these 2 to the n possible states. Although in the course of the computation, it's gone through this incredibly complicated Hilbert space with many, many dimensional. At the end of the day, you just end up with one state, and depending on which of those states it's in, that will give you the answer to your computation. And a very important realization was achieved by Shaw in 1994. You can use this scheme in principle to factorize an n-digit number. If you use a classical computer, then at least as far as anyone knows, the time you would take on a classical computer is exponential in n. For a quantum computer, at least in principle, it's only a power law in n. So that means that all sorts of processes like this factorization, which would be totally unthinkable for a classical computer, could be done in a reasonably short time by a quantum computer. Okay, how are we doing for time? Let's see. Okay. Well, in the last part, well, let me go on to the next slide for the moment, please. Next slide, please. Here's the simplest design for a quantum computer. You couple together n being a fairly large number in general, two-state systems, so-called qubits, in such a way that we can reliably perform one qubit operations, which are non-entangling, and also two qubit operations, which in general are entangling. An example of a two-qubit entangling operation is if I start off with my in a non-entangled state, up 1, down 2, and then let the system be acted on by a Heisenberg interaction, J sigma 1 dot sigma 2, then after a certain time, I will produce that state 2 to the minus a half, up 1, down 2, plus I times down 1, up 2, which is clearly entangled. So this is the very basic principle on which a quantum computer works. Now we have a certain number of requirements for the so-called qubits, the elements of a quantum computer. It have, for simplicity, it should have only two states available. It should be easy to initialize and also to read out the result from. It should be scalable, and most importantly, it should be adequately decoherence-free. What does that mean? Well, if I have a superposition, a quantum superposition, like the one indicated in the equation at the top, then as long as the system is completely isolated, that's fine. That superposition can continue as long as I wish. However, no system is ever completely isolated, and generally speaking, it's in contact with what we call an environment. And the effect of that environment is, very crudely speaking, going to be to start screwing up the relative phase between the two parts of that superposition. And this is the phenomenon known as decoherence. So in order to make your quantum computer work, you better not have too much decoherence. And a characteristic figure of merit for this is what we call Q sub phi, which is the product of the characteristic frequency of your two-state system times a dephasing time relative. A viable quantum computer, to the best of my knowledge at least, unless it's been recently updated, is that you do really require a Q sub phi greater than about 10 to the 4. And when people started seriously thinking about building a practical quantum computer in the late 90s of the last century, they automatically thought, well, we've got to have some microscopic system which is very well isolated from its environment. So they thought about systems like nuclear spins and trapped ions and so forth. These are simply not interacting very strongly with their environments, and therefore it was hoped that you would reach this kind of figure of merit. One thing, however, which has been really remarkable in the last 20 years is that people have realized that there are also genuinely macroscopic, or at least mesoscopic, certainly mesoscopic systems, which can also satisfy this requirement. And the case in which I've been personally most interested in is what is called a flux qubit. It's a particular kind of Josephson device. I won't go into the details right now since time is getting short. But if we could, I'll just show you very briefly a picture. I think that's on the next slide. Next slide, please. Yeah, here it is. This is actually a picture courtesy. Yeah, just go back to that for a moment, please. Well, okay. Okay, you don't really want to know the details of this, but this is what such a device actually looks like in real life. This is courtesy of my experimental colleague Dale van Harlingen at the University of Illinois. And the active element in this is actually this little bit down here, which is blown up down here. It's just about visible with the naked eye. you're actually talking about two different states of this macroscopic object which undergo a quantum superposition. Can we just go to the next slide? I'll ask you to skip 2 or 3 slides, I think. Yeah, skip this one. Skip this one. Skip. No, this one I'll keep from it. So very crudely and simplistically, we can imagine this flux qubit to be a ring, a superconducting ring, which has a flux through it. This is close to a flux qubit. It turns out that in a superconductor, the basic particles or effective quasi-particles are so-called Cooper pairs. That's 2 electrons, pairs of electrons, 2e. And they are described by a variable which is the circulation, the integral of the Cooper pair velocity around the loop. And it turns out that can only be given by an expression of this type. I've been going rather fast here, so you have to take some of what I'm saying on trust. The energy of such a system is proportional to k squared. So n minus pi over phi 0 squared. Phi 0 here is the flux quantum h over 2e. Now, if the flux through the ring is 0, that's not very interesting because the ground state is unique, all the pairs are at rest. If the flux is half flux quantum, then the ground state is doubly degenerate. You can either have n equals 0 or n equals 1, and that corresponds to either all of the pairs rotating clockwise or all of them rotating anti-clockwise. And now the crucial point to realize is that you can't, as it were, split these. You can't have half of the pairs rotating clockwise and half anti-clockwise. That's strongly forbidden by energy considerations. Well, this is not quite a flux qubit, but it's getting close to it. So let's have the next slide, please. Yeah. Okay. This is a Josephson qubit. All we've done is to take the superconducting ring, which I had on the last slide, and put into it a Josephson junction. And if you're not sure about what a Josephson junction is, just think of it as a sort of gate which will transmit Cooper pairs but with increased difficulty. And it turns out that in that situation, quantum mechanics tells us, and this is not at all trivial, it took a lot of work over the 20 years between 1980 and 2000 to really reach this conclusion with any degree of confidence, but it turns out that the possible state of such a flux qubit is a quantum superposition of all the pairs rotating clockwise and all of them rotating anti-clockwise. Notice this is not the same as saying that half of the pairs are rotating clockwise and half anti-clockwise. You have a genuine quantum superposition of these two pretty much macroscopically different states. The evidence that you have such a state is obtained either from, well, originally from spectroscopic experiments, I won't go into the details of those, subsequently from real-time oscillations, rather like the oscillations of the ammonia molecule between these two states. In those early experiments, the figure of merit was only something like 50 to 100. That was that's 20 years ago. Already by 2018, and certainly by 2020, the figure of merit for such flux qubits is way over 10 to the 4. So they really do, these macroscopic systems with macroscopically distinct states really do satisfy the conditions to build a quantum computer, and people have started quite seriously trying to do this. Google, there's a famous paper by the Google group, research group, about 18 months ago now, I think, where they actually managed to entangle, or claimed at least to have entangled, I think actually 70 qubits. Incidentally, there were as many authors on the paper as there were qubits. There were more than 70 authors on that paper. But anyway, people really are getting down to the nitty-gritty and building at least primitive quantum computers using these genuinely macroscopic objects, these flux qubits, Josephson devices. So I think you can see that in the 56 odd years since John Bell's original work, what was originally the most abstract possible theoretical considerations have now been transformed into what has become a multi-billion-dollar industry. And I think that's really an amazing story. Thank you.
So thank you, Professor Leggett. And now the floor is open for questions. So some questions are here and people can raise hand and ask. And some questions are in the YouTube channel where most of the students are there. So they are also posing some questions in the chat room. But to begin with, I can see two hands are raised. I request Professor Dipankar Home to unmute himself and ask the question. Professor Home, please.
Yes, Tony. So thanks for a very illuminating, as usual, your very simple talk with a lot of perceptive observations. So I'm just curious to ask at this moment two questions, which may be of all interest to the wider audience also. The first question relates to the latest experimental tests of Bell's inequality that have been done and for a loophole-free test. To what extent do you think the locality loophole has been plugged in these experiments, taking into account the point about the ambiguity or imprecision involved in specifying when a definite measurement outcome can be regarded as realized, a point which you had been making in your earlier writings? So that is one question. And the other question is about what is your comment on the significance of testing Bell's theorem or entanglement for massive objects in the context of the enterprise? You have yourself pioneered for testing quantum superpositions in the macro limit and objective collapse models relative to the measurement problem. So if all these experiments continue to confirm quantum superposition in the large mass limit and rule out objective collapse models, what would be your position vis-a-vis the quantum measurement problem?
Okay. Well, hello, Dipankar. Okay, as to your first question, I'm sorry, my mind's gone blank. What was your first question again? Very, very briefly. What was? I'm sorry, I have a blank out. My mind has gone blank. What was your first question?
Dipankar, kindly unmute yourself once again and speak one by one.
Yeah, just very quickly, very briefly, remind me what your first question was.
So can you hear me?
Yes.
So the first question was about how to what extent do you think the locality loophole has been plugged, taking into account the point about ambiguity in specifying when it's a definite outcome.
Indeed, good. Thank you. I don't know why I didn't remember that. Okay. Well, let me just explain. Any analysis of the so-called EPR Bell experiment has to make some assumption about when it is that a particular outcome is definitely realized. So let's just go to the case for a moment, the case of a single photon incident on a measuring apparatus which consists of a polarizer plus a detector. At first sight, you'd say, well, the photon either does or does not pass the polarizer when it gets to it. So that's the definite event which either occurs or doesn't occur. But now, unfortunately, you realize that's wrong, because there are other kinds of experiment in which you can actually show interference between the transmitted and the reflected states of that same photon. So no definite outcome has to can have arisen when the photon strikes the polarizer. Okay, well, if the photon was transmitted, then it'll go into some kind of detector, and typically this might be a photomultiplier. You would excite some electrons, and these then would excite other electrons. There'll be a sort of avalanche effect. So you say to yourself, well, maybe it was when that avalanche occurred that things became definite, that one outcome rather than the other was realized. In other words, either the avalanche occurred if the photon was transmitted, or if the photon was reflected, no avalanche occurred. But again, unfortunately, that's not what quantum mechanics tells you. Quantum mechanics tells you that you still have a superposition of states of the universe in which the avalanche has and has not been triggered. The detector has and has not fired, and so on. And so until you actually come to the to direct observation by a human subject, you cannot really say that any event has definitely happened or not happened. This is a leftover difficulty, as Dipankar pointed out, with even the most sophisticated experimental tests of things related to Bell's theorem. I think, in principle, it would be possible to resolve that, provided that you're not a believer in the so-called many worlds interpretation of quantum mechanics, which I most certainly am not. In principle, it should be possible to resolve that by doing experiments with human observers in satellites in such a way that the transmission time between the two measuring stations is much longer than the reaction time of the human perceptual system. Under those conditions, you could say that you have eliminated that so-called collapsed locality loophole, but until then you really haven't. And so I do think that it's very well worthwhile to try to pursue further experiments along those lines and make quite sure that everything is completely firmed up. I think most people would bet that you'd still get the quantum mechanical results even under these hypothetical extreme conditions, but we really do need to do the experiment if it's at all possible. And there's some very remarkable advances made, for example, by Professor Pan Jianwei's group in China, which suggests that it may not be that many years before we can actually do this kind of experiment.
And the other question, Tony, was in relation to that. What would be your comment on the significance of testing Bell's theorem or entanglement for massive objects in the context of testing collapse models or superposition principle? And then if the experiments continue to confirm quantum mechanics, then what will be your position? And rule out collapse models, what would be your position with regard to the measurement problem?
Okay, thank you. Yeah, well, certainly I think it's very important to continue doing experiments on quantum superpositions in macroscopic systems, because after all, that is what brings us closest to our own direct experience. We actually, at the University of Illinois a few years ago, we being actually my colleagues Paul Quiert and Wang Ranxia, I was just a sort of matchmaker there. We started an experiment to see if the human visual system can be put in a superposition of two different semi-macroscopic states. It turned out that the experiment was not really practical, simply because the human visual system is such an inefficient detector. It would have taken much more than the lifetime of the graduate student involved to get any meaningful results. So, but I think it is very important to push along that and similar lines. Now, Dipankar asks, suppose that these experiments are done to an arbitrary level of macroscopicity, complexity, etc., and still continue to confirm the quantum mechanical predictions. How would I react? And I think my only reaction, the only possible reaction I can see is to take what I call the extreme statistical point of view. That is to regard the formalism of quantum mechanics as simply nothing more than a recipe. Simply a string of symbols written on a piece of paper, which will enable us to start from a given experimental setup and make predictions about the probabilities of different outcomes. And beyond that, in some sense, you really shouldn't attribute any physical reality to that formalism at all. So when, for example, in the Schrodinger's cat, the famous Schrodinger's cat thought experiment, when the cat, or more precisely the universe containing the cat, is described by a quantum, formally by quantum superposition of a state in which the cat is dead and a state in which she's alive, then all that set of symbols means in the quantum formalism is that if I now inspect the state of the of this particular cat, I will find a certain probability for her to be dead and for her to be alive. And that's the end of the story. You should simply not try to interpret the quantum formalism beyond that. That's a very uncongenial point of view, and I hope that I never have to, I don't have to take it. But if in fact the experiments were to confirm the quantum predictions at levels arbitrarily close to our own direct consciousness, then I think that's the conclusion I'd have to come to.
So before we take, I can see a couple of hands are raised, but before we take questions from here, I'm taking one question from the student side. So RV Misra has asked in the YouTube channel that is a long question, but in short, that would you like to comment on retrocausality, and if there are non-locality over space, why can't there be temporal non-locality?
Okay. That's certainly a very interesting question. I tried to think about somewhat. Certainly, one possible way out of the conclusions which are normally drawn from Bell's experiment, from the Bell EPR experiments, would be to reject the principle of what I usually call the principle of induction, though that's probably a bad name, the usual error of time. In other words, to assume that under certain conditions, events which take place in the future could affect the state of systems in the present. It's a very, very slippery topic, I think. As with all the most really difficult questions in physics, the difficulty is not to answer a well-posed question, but simply knowing what question to pose in the first place. And I have found it very difficult to ask concrete, definitive questions concerning the error, so-called error of time. But there has been there's a relatively substantial minority of physicists who have been thinking about that. The late Olivier Costa de Beauregard in Paris was one person who spent a lot of time thinking about a version of theory where indeed you can get so-called retrocausality, that is, the future can affect the present and the present can affect the past. All I can say, frankly, is that I find it very puzzling, but I do in fact suspect that even when we come to a satisfactory resolution of the quantum measurement problem, then in some way or another it will involve a very radical revision of our notions concerning retrocausality. But beyond that, I'm afraid I really don't have anything intelligent to say.
Himanshu Agrawal has also raised hand. I request Himanshu Agrawal to unmute himself and ask the question.
Thank you, sir. Thank you. Question is related to slide number 5.
Can we perhaps display slide number 5? Okay, good, yes. Yep.
Yes.
So Himanshu, continue with the question.
Yeah, in the last line, that psi equal vector x2, vector x1, vector y1, vector y2. So question is, what is the dimension of vector x1, x2, y1, y2? And second is how this product is defined, vector x2, vector x1, how this product is defined.
Okay.
Last line.
Yeah. Okay. Yeah. Well, I could rewrite that perhaps as psi equals phi sub x of variable 1 times phi sub x of variable 2 plus phi sub y 1, etc., etc. I'm not quite clear of the nature of the question you're asking here. I mean, one normally thinks of the wave. Suppose I simply have a product state.
Sure.
So we just consider the first term, x1, x2.
Sir.
One normally thinks of the two-particle wave function as a product of functions of only variable 1 and only variable 2. I'm not quite clear what is the difficulty that you.
So probably he is asking that means which kind of product and its tensor product means.
Which kind of product?
So this is a tensor product.
Okay.
Well, as I say, if it helps, I could write it out as phi sub 1 phi sub x of 1 multiplied by phi sub x of 2. Then it's just a simple multiplicative product, nothing at all fancy. I'm afraid I'm not really understanding the nature of Dr. Agarwal's question here.
Okay, so we can move to another question. Anindo De has written a long question in the chat. So I would better suggest Anindo to himself ask the question. Anindo, can you unmute yourself and ask the question?
Okay, I am telling Professor Leggett. Recently in HAP Nobel lecture, Professor Stephen Winbach remarked that no one has found a way to state the postulates of quantum mechanics without bringing the existence of observers into the postulates. I am not sure whether quantum mechanics will survive in its present form in the coming centuries. Some bodies are looking for departure from quantum mechanics. How will you comment on that, Professor Leggett?
Well, I agree. I can simply say I agree. I'm interested that Professor Weinberg, whom I understood for many years to feel, for many years I thought that he felt that there was no particular problem in the quantum measurement situation. It's I find it interesting that he now certainly does feel there's a problem, and I agree with that.
Himanshu Pandey also raised his hand. Sure. Dr. Pandey, can you unmute yourself and ask your question?
Yeah, Professor Pathak, I have a question related to slide number 8. So could you please show slide number 8?
Sure.
We need 8.
So here is.
Yeah, please. Yeah. So actually, I might have missed the point which Professor Leggett was describing here. So just in the second line, second last line, the last term is having a minus sign. I might have missed this particular point. Whether means, could you please comment on that? Why this this minus sign related to BD?
Oh yeah, sure. Well, of course, one can consider any number of different combinations. You could have, say, AC minus AD plus BC plus BD or whatever. there are a number of possible combinations you can make, but only some of them have the property that the predictions of objective local theories are contradictory to the predictions of quantum mechanics. This particular combination is not unique, but it's just a useful one to consider.
So here means we can take anyone as a with the negative sign.
Yeah, sure. I mean, you could have, say, AC minus AD plus BC plus CD, and basically everything will work out someone. Yeah.
Thank you, Professor.
What you can't do is, well, you can. I mean, you can consider, say, 4 plus signs, but all plus signs, but then you wouldn't get an obvious contradiction between. At least I don't think you would. I can't think it through my head. Between the predictions of quantum mechanics and those of objective local theory.
Thank you, Professor.
Okay.
So I could not see Professor Archan Pramanik. He was also raising hand, but now I can see Professor Apurva Patel has raised his hand. So I request Professor Patel to ask his question.
Okay, I want to know your opinion about 3-particle correlations like the G at Z states. The reason is that you can make deterministic observations for G at Z states where classical and quantum predictions are different. And so you do not have to worry about probabilistic interpretation and ensemble average and things of that sort. You can have a single short experiment where quantum and classical predictions differ. And that gives a more explicit demonstration of what is different. Do you have any explanation of those kind of determinations of quantum mechanics?
Well, sure. I mean, I think the GHZ idea, the idea that you use 3 particles to avoid having to deal with probabilities and so forth, it's a very important one. On the other hand, one has to realize that in real life, the way that probabilities come in is not simply, as it were, through the theory, but also through the experiment. You're always going to get a certain amount of jitter in your in the actual experimental outcome. So you don't, in fact, entirely get away from having to use probabilities in the interpretation of those experiments. However, it does remove a substantial amount of statistical considerations which are otherwise unavoidable. So yeah, I think certainly that's an important development.
So now I would like to ask Kishore to summarize the questions which are asked in the YouTube link. So Dr. Kishore Thapliyal, can you summarize some of the questions, meaningful questions from the YouTube link?
So some questions are already answered, like this locality loophole. And the other question which is still unanswered is one question which is very basic question about, is it okay to consider linear entropy as an entanglement measure, as was done in the context of Hubbard model? And the other question that is it true that a quantum computer can give all possible results of a problem due to quantum superposition, which we cannot do with the help of our traditional classical computers? And other students have just asked general questions why classical computer wouldn't be replaced by quantum computers in future.
Okay. See, sorry. I'm afraid.
You ask one by one, Kishore.
Yes. I think perhaps you can just ask one by one.
Yeah. So
the first question was what again?
about linear entropy as an entanglement measure, as was done in context of Hubbard model?
Well, yeah, I mean, the whole question of defining a quantitative measure of entanglement, I mean, certainly that's been a subject of a lot of discussion in the literature of the last 20 years or so. But I frankly feel there's not a great deal of point in spending a lot of effort defining a quantity like, say, three-particle entanglement without a specific context. If you have a specific context in which you're going to you want to try to use it, then I think it may make some sense to pay attention to the details of a precise definition of entanglement. But simply to argue about it in the abstract seems to me not, in fact, a terribly useful exercise. So I'd want to know, you know, for what purpose was this definition of entanglement going to be used before I could answer the question.
We move to the next question.
Next question is by Sudaman, which is how can we devise experiments of non-invasive measurements?
Well, I mean, in some sense, the point one could say that the brilliant point about Bell's work is that he managed to use the locality principle to formulate the idea of, implicitly at least, formulate the idea of a non-invasive measurement. But of course, it's very difficult to use that if you're dealing with, say, macroscopic objects like flux qubits. The best you can do, and this is something which was actually done in an experiment in which I had a small part a few years ago, is to simply do a series of preliminary trial runs in which you actually try to establish whether making a so-called negative result measurement at a particular time affects the statistics at a later time. If you put some bound on the effect of this negative result measurement, very crudely speaking, what is a negative result measurement? Well, very crudely speaking, if you think about it, say in the context of a young slits experiment, then you would shine a flashlight on one of the two slits, and you would throw away all runs in which you actually saw your electron coming through that slit, but you would keep all the runs in which you do not see it come through there. And you'd argue that by shining your flashlight on one slit, you could not have affected the passage of the electron through the other slit. Now, what we did in this is an experiment conducted at NTT a few years ago on flux qubits. We did an experiment where essentially we tried to detect the system when it was in one state, but not when it was in the other, and we threw away all those runs in which we did detect them. And then we looked to see whether that affected the subsequent statistics. And having done that, we could then go on to the real experiment and use the postulate of non-invasive measurement, or at least we could partially non-invasive measurement to set a bound on the possible errors due to the measurement. I'm sorry, that doesn't sound very coherent, I'm afraid, but I think undoubtedly the ideal thing would be to, in some sense, dispose of the idea of non-invasive measurability in favor of that of locality. In other words, to do experiments on macroscopic bodies like flux qubits, where the measurements are literally separated by space-like intervals. As far as I know, at least, that has not so far been done, but it may not be that far in the future.
So probably the last question left was the student asked that why a quantum computer will not replace classical computer in near future.
Well, I think this raises the question of so-called quantum supremacy. The idea is that you should be able to find at least one task in which you can demonstrate quite explicitly that a quantum computer can outperform a classical one, the best classical one. It's now claimed that this has been done in some very specialized problems for which a specially built quantum computer can outperform a general classical computer. However, what is, to the best of my knowledge, has not been done is to show that a quantum computer, a purpose-built quantum computer, can outperform a purpose-built classical computer. So I think for any one specific application, it may be possible to build a quantum computer which does demonstrate this kind of quantum supremacy, but certainly we just right now, I think, don't have the equipment to build a general purpose quantum computer which can outperform a general purpose classical computer. It perhaps will be done. The only question in my mind is, will it be worth it? That is, will the cost in actual money and human time, effort, etc., will the effort needed be so extreme that in the end we decide it's just not worth it? That is, we don't need to build a general purpose quantum computer. We can just build special purpose ones for very specific tasks, and that'll essentially be the end of the story. No one will feel it necessary to go beyond that. I think that could easily happen.
I can still see that Dipankar Da has raised hand. So if Dipankar Da has another question, kindly ask Professor Dipankar Home, please. Professor Home, do you want to ask another question?
Hello. Yes. If there is time, just a minute. So, Tony,
okay.
So what is it with these objective collapse models that had been proposed for testing the collapse for the resolving the quantum measurement problem? So these macroscopic tests of quantum mechanics, they put bounds on those objective collapse models. So what is your view on this enterprise? This suppose all these objective collapse models, to what extent they can be really ruled out?
Yeah. Yes, I think the problem is that the general idea of an objective collapse model is, of course, fairly easy to formulate, but it's much more difficult to decide whether one version is something more plausible than another. For example, probably the best known example of a objective collapse model is GRWP, Girardi, Rimini, Weber, Pohl, but that relies on the trigger for the collapse being the separation of the center of mass of a system. And for all sorts of technical reasons, it's rather difficult to do experiments along those lines. It seems to me that there's no particular reason to prefer that kind of model vis-a-vis a model in which, say, it'd be the difference in electrical currents which will trigger the collapse. So I think one simply has to try to push ahead on as many different fronts as possible. That is to try to do experiments which test the
So you're not audible. So I guess Professor Leggett has lost connection, means I cannot hear him. Professor Leggett, kindly unmute yourself. You are mute. Kindly unmute yourself.
Oh, okay.
Okay.
Yeah. Okay, is that the end of the questions? Is that all the questions?
Yes, but the last question was asked by Professor Holm, which you have addressed, and then somehow it was disconnected. So is there anyone else who want to ask any question? I don't see any hand raised. So if not, it was a very wonderful evening and of course a wonderful morning at Professor Leggett's place. And this finally worked. Actually, we started talking about a potential visit at our institute at the time of a meeting where Dipankar Da and Archon Da was organizer. It was 75 years of entanglement in Calcutta. And we discussed a possibility that Professor Leggett on his return from Delhi visit us. And because of some network issue, it would not become possible. But finally it happened, although in web mode, but that we could organize a talk. And the best thing is that many students could attend and they can ask questions from many places. So I would like to thank Professor Leggett for kindly agreeing to accept our invitations. And I would also like to thank everybody who participated in the discussions in the talk on behalf of both National Academy of Sciences India's Delhi chapter, as well as Department of Physics, JP Institute of Information Technology. Thank you very much. And we finish this evening talk here. So thank you, Professor Leggett, once again.
Thank you. Thank you. Goodbye. Bye.
Bye.
Bye. Bye. Bye.
Bye. Okay, I'll leave it.